out, yeah. Okay. All right, welcome to the New York City Category Theory Seminar. Tonight's speaker is Jonathon Funk, who's going to speak about isotopes.
No.
No. Sorry. Hold on. Don't move. Don't move. Don't move. Pseudogroup torsors. Sounds good. And take it away.
So what do I do?
Oh, you have to share screen on the bottom. I made you the co-host. You see it says share screen?
Yeah.
So you have to do that.
Did that.
And does it let you share?
Select a window, it says.
Right. So what is the paper that you want on the thing?
Yep. It's there.
Okay. Okay. It's a pseudogroups on it. You got it.
That's it. I want to also share the. Oh, can you see that notebook?
No, I don't see that notebook yet. Hold on, I'm pressing pause on.
I'll just go back and forth, I guess.
Yeah.
Huh. I didn't realize that. I thought I could just share my whole screen, but.
You can. It's just too hard to sort of do tech support at the moment. So.
You can do that?
Yeah, most people do that most of the time. So there's a way to do it. I just can't tell you exactly how at the moment because it's too complicated.
So you see the whiteboard here?
Yeah, we see your pen and everything, yeah.
Okay, I'll do the whiteboard. I'll have to make notes separately on the whiteboard.
Okay, go.
So I'll just use the whiteboard that's here. And I'll begin with our paper, which I have. I don't need this other application. Let me just close that. I'll go full screen.
Let me just double check. When you go to share screen, there's nothing that says desktop?
Yeah, no, nothing, yeah.
Okay, I'm looking at their support site and you can usually pick desktop or a specific app. And so I don't know.
Yeah, right.
All right, sorry. I'll let you.
I just go to new share and I should see the option to do desktop, but I don't see it. So that's that. I don't know. I don't know how to do it then.
Gershom, do you think if I made him host, that would be helpful? But then he would have to do the recording.
Oh, I don't think it would be. There's just something with his software, and I think.
Okay, go. Okay. Anyways, go on.
So you see, you're looking at my paper now, right? Our paper, right?
Yeah, yeah.
So Peter and I, in the last year or so, have written this paper. Why did we feel there was a need for such an article? Maybe I can explain that in the process. But
I think you should start with saying what a pseudogroup is.
Yeah, I'm not going to get into technicalities right away. Okay.
Okay, so fine. You're on your own.
Yeah. That's more like I will.
Okay, good.
Intuitively, what is a pseudogroup? It's kind of, let me go to the whiteboard. Yeah, it's not bad for me to just go back and forth between the two, I guess. For now, before intuitively, what is a pseudogroup? It's like an algebraic prescription. I know this is kind of vague for a local space. If you want. How's that for a definition? Now, one thing I should say, I guess, what are these things down here? Oh, I see. Okay. Anyway, feel free to interject or make any comments you like. I'm going to actually switch between this whiteboard here and then the paper itself. And that's sort of intuitively what a pseudogroup is in an algebraic sense. I can, if you like, provide a mathematical definition. But I want to give a more kind of historical, at least recent history about this subject. And then for that, let me go to the bibliography. Of our paper. Everybody's looking at the paper?
Yes, yes.
Okay. I'll go down to the bibliography here. And there are a few articles here I'd like to mention that are sort of pivotal or influential in this subject. Number one, I'd like to highlight things. At least I can highlight, and I would really wish I could write on the PDF, but the best I can do is highlight. Marta's paper, going back, that goes back to 1990. And then Peter and I wrote a paper in 2010. This paper is important. And then the next one I'd like to mention is this one by Koch and Mordig, Presentations of Étendue. And then down here, Mark Lawson and Lentz, Pseudogroups and their etale groupoids. And also finally, Pedro Resende's paper, 2007. All these articles are important in the recent history, and they're important in the way they inform the present article that Peter and I have recently written. So what's this down here? I'd like to just clear this. What is that? Did I just?
Yeah, you cleared it.
Yeah. Oh, back. Oh, I just went forward. Very good. Yeah, that's what I wanted to do. Yeah. So let me just write those papers there that I pointed out. Marta Bunga's paper. Now, remember this, this is very much a topos theory endeavor here. There's a lot of topos theory. Marta Bunga was interested in understanding what are the points of a localic groupoid. So if G is a localic groupoid, B of G is its topos of etale actions, and G would be a localic groupoid. So I'm just trying to give you a little overview of recent history and the important articles that inform our paper. She proves for actually any localic groupoid, what you might call localic models. So this would be a localic topos X locale. And proves that this is this topos classifies a certain notion of torsors over X. Then next,
John, are you going to tell us what a torsor is?
It's first of all, it's okay.
You can say no, but I think it would be helpful.
Yeah. A torsor is a left action. Here, the objects of these are right actions. Etale, the objects are etale objects with a right action and a total right action by the groupoid. So that would be the objects here. What is a torsor? A torsor likewise is a fibered thing over G, but it's more like it should be, if that's perceived as a right action, this would be perceived as a left action, but it's flat in the sense, it's a special kind of action. Well, I used X here, I shouldn't have, X is that, maybe T. Flat would be locally free and transitive action. So actually, I don't want to go into it any more than that. But what I want to say is here that the emphasis is on localic models and isos between them. So isomorphisms here. Or I shouldn't do it like that. Pardon me. That would be an object would be a torsor, and the category would be, the morphisms would be isomorphisms between them. Isomorphisms. So that tells you that here, the two cells will be restricted in this category. So you'll have a category of all the objects would be geometric morphisms like this, and two cells between them, but only the isomorphisms. So I point that out because the theory that Pieter and I developed does not have these restrictions. Yeah. Anyway, okay, let me move on here to the Lawson. The next article that comes to mind, oh, well, it was the article by Pieter and myself. And very much our present article is in some sense a sequel of that. And here we developed a notion of torsor of an inverse semigroup in general, which would be a thing like this. I'm using X again, but not the other X. A pseudogroup has an underlying inverse semigroup. So you know kind of the neighborhood we're in, inverse semigroup. That gives you the kind of algebraic kind of substructure we're talking about here. So I'll come back to that.
John.
Yes? Hi.
Can I make a suggestion?
Uh-huh.
If you explain how G sets classifies G torsors, the examples you give now can be seen as generalizations. I know you want to start with the hard part first.
That's another talk. Okay, yeah. Yeah. Well, that would be a very good thing to do. But I didn't prepare to do that, though. But
yes, it would be sensible, eh?
Hey?
It would be sensible.
Yeah. Yeah, for instance, this localic groupoid could be a discrete group. Yeah, could be a discrete group, for instance. And then in that case, a torsor in that case is just the usual thing that you think of, that you know. A torsor on a discrete group is a locally free, transitive, non-trivial action. That's what that is. So getting back to the recent history, also the Koch-Mordic paper is quite important. This I listed as one of the influential papers anyway, because here we have a site analysis or a site prescription It's very prescription of étendue, what are called étendue. Étendue is like a local space that I mentioned before. And this is very much related to pseudogroups, even though it's not at all mentioned in their paper, and that's not their angle. They do not talk about pseudogroups, but it's close. It's very close to pseudogroups. So that's 3. 1, 2, 3. There was 5. There's then I think I should mention Pedro Resendri's book, his article on what he called the germ groupoid of a pseudogroup. Let me denote that as G of S. The germ groupoid. Of a pseudogroup, G of S, of a pseudogroup S. So this happens to be an etale groupoid. So it's an important connection between pseudogroups and localic groupoids. But as you know, there's, of course, a well-known topos connection between localic groupoids and toposes that I've already mentioned right here, BG, the B construction, or the so-called classifying topos of the localic groupoid. So that's 4. There's one more influential article that I haven't mentioned yet. I want to mention it here. I'll have to squeeze it in here. The Lawson-Lentz paper. I had to mention Pedro's paper first because Mark and Lawson and Lentz, they study the points of the germ groupoid. And that is a spatial groupoid. It's a continuous groupoid, and it's an etale groupoid, a continuous. They study thoroughly this connection, the points of that. So these are 5 influential articles in the recent history of this subject. What stands at the center is this concept. It's the unifying concept. Believe it or not. At least that is the way we perceive it, for today anyway. They all inform this concept and vice versa. This concept of an action of an inverse semigroup on an object X, a set X.
What's the I of X again? What's the I?
Okay, thank you for the question. Let's turn to some of the details. I'll expand on that a little bit, since what I'm going to be talking about, our paper, now focuses on this notion. This notion of an action formulated in this manner. So I will go to a new page now for that. What's this? Oh, 3. Okay, page 3. Yeah. Let's have a look at this. What is this notion? S for now can be an inverse semigroup. Okay. Now, if you're not familiar with inverse semigroups, what is an inverse semigroup? It's sort of the unifying or a common concept. It's a unifying concept for, I would say group and then maybe an imp semilattice. Although it's interesting, you do not get every inverse semigroup by combinations of these. Not quite, I don't think. But in some sense, it's an encompassing concept for these ideas. Anyway, every element has a local inverse. So there's a unique inverse, which I denote S star. Yeah. For all S, there exists unique S star, such that. So this, what is Ix here? If X is a set, then this is an inverse semigroup. It consists of all partial bijections from the set X to itself. So you may picture that as a subset of X mapped by a mono back by some monomorphism back to X. So it's a partial bijection on X. So it's a bijection between A and the set and its image M of A. So these combine in a, M is an element. A thing like that is an element. It's called the symmetric inverse semigroup on the set X. There's no more structure than that. So M star, that's the M. You may wonder, what's M star? Well, M star is this. Its image and then the inverse map. That is M star. And composition is given by the usual span. Let me call it that, span composition. Yeah, that's an inverse semigroup. The interesting thing is this Ix is a pseudogroup, actually. And Ix is a pseudogroup. Did we have a question or?
No, but now you're going to say what a pseudogroup is?
Yeah.
All right.
I'm going to illustrate it in the case of Ix. So maybe another page would be suitable for that. I like this. I got as many. All the pages are saved, so you can ask any questions about anything. Ix is a pseudogroup. That's important. And now I'll try to say what a pseudogroup is. It's also a pseudogroup in the sense that it has it doesn't have arbitrary joints. You can't take so if I had a whole bunch of these things, elements of X, say I had a bunch of them, a set of them or something, a collection. I'd want to take their supremum, right? Oh, not for supremum. Does it exist? No, of course, it doesn't always exist. You can't, I'm thinking that it should just be the union of these AIs, but of course, that supremum isn't going to exist in general, will it? Because the MIs may not agree on the intersections and so on. So the MIs may not be compatible. But if the family is compatible in that sense, then indeed, a supremum does exist. I won't go into technically what compatible means in the general inverse semigroup. We can get into that later if you want, but anyway, this does exist. Okay, but the maps themselves would have to be compatible, meaning they would have to agree on their intersection, right? In order to get a supremum. Anyway, yeah, so that's what you want. You want compatible supremum, and you want the multiplication to distribute over these. You want it to be, you want it to cooperate. Sup should cooperate with multiplication. What, of course, right?
Yeah.
That's a pseudogroup. That concept that I just explained in the case of IX is more generally what a pseudogroup is. Yeah. So generally a pseudogroup is an inverse semigroup with compatible suprema that are cooperate with the multiplication. Yeah?
Yeah.
That's a pseudogroup.
Can you say it in terms of this S star, S and S star? Does the S star not necessarily have to exist? Is that the point?
No, that's the inverse semigroup structure. S star is the inverse, is the local inverse.
I understand. So what's the relationship between a pseudogroup and and an inverse semigroup?
Yeah, that's a good question. For now, all I'm going to say for that is that, by definition, a pseudogroup is an inverse semigroup with compatible joins that cooperate with multiplication. That's the definition.
Okay.
So it has an underlying inverse semigroup, right? It's a pseudogroup, definition of a pseudogroup. Some authors would call this an abstract. The experts might call that an abstract pseudogroup. I don't know. Because you can play around with this. There are variations on this theme now. X could be a space, topological space, and instead you could talk about open subsets and homeomorphisms. Okay, that would also be, I think, a pseudogroup. That would be more an example of a concrete pseudogroup. Anyway, a pseudogroup is an inverse semigroup with compatible joins that cooperate with the multiplication. I don't know how to say that. With the multiplication. Okay. That's what a pseudogroup is. That's an abstract definition. Or what some people call abstract pseudogroup. So it's sort of like, you can see that these things are sort of like charts for they're giving a prescription for a space, but it's not a space in general. It's more like a local space, that these charts have to be glued together and you create a space out of this thing. That's the topos B of the pseudogroup. So that's the first point in our paper, is we want to understand, what is this? What is the topos of a pseudogroup? Yes. So that is our first goal in the paper. It's the first thing we achieved. And maybe I should go now back to the paper. I don't want to get too into the technicalities, but anyway, any questions? I would like now to just say what we did in this paper. Here's the abstract. We did basically two things. We analyzed this connection between pseudogroups, groupoids, and toposes. So like I say, there's a lot of history to it, and much has been done. So the first thing we understand is that since Resende has shown us that they're associated with a pseudogroup is a localic groupoid which he calls the germ groupoid, and every localic groupoid has associated with it a topos of etale actions. There is therefore a topos of a pseudogroup. But it's a question of understanding what is this topos exactly. And that is our first aim. That was our first goal. That we achieved in this paper. And the second is we analyzed closely the passage from pseudogroup morphisms to geometric morphisms. In other words, we gave it a more categorical treatment. And in the process, we discovered really that there's a nice bicategory, in hindsight anyway, the bicategory of flat bimodules between pseudogroups. So the paper itself, I will not get beyond the introduction today, but in the paper itself, let me make a little overview of the paper. We provided a significant amount of background and background material. In fact, half the paper is devoted to that, to providing some background material. And in fact, it's only halfway down that we get into the topos of a pseudogroup. And then we explain what that topos does classify. In terms of, you might call flat bimodules, or a torsor would be a flat action. But it's got to be more, if you're talking about pseudogroups, it's going to be more than just a flat action. It will also be a local action. Because of the supremum condition. Anyway, here's maybe if I'll read a little bit of our introduction. This idea, by the way, of abstract pseudogroup goes back. I didn't talk, this is the prehistory. I was just speaking about the recent history, but of course, the idea, if you want, I don't necessarily know that much about the very old history, but Mark Lawson has explained that in his paper, that this concept of pseudogroup essentially comes out of differential geometry, going back to Lie and Cartan, etc., and so on. So let me go to a picture. I guess we need a diagram now. There's, while I'm here, let me point out what is the germ groupoid of a localic, of a pseudogroup, as defined by Pedro Resende. The locale of objects. Remember, a localic groupoid is a groupoid in the category of locales. Its objects is the frame itself of idempotence of the inverse of the pseudogroup. That forms a frame in the pseudogroup case. The idempotence of a pseudogroup form a frame. And its locale of morphisms consists of the collection of downsets of S which are closed under suprema of compatible families that I was talking about. So this is a way of making locales. Yeah, it's it's a frame quotient or a sublocale. It's a way to prescribe a locale. or present, it's a way to present a locale as collections of downsets which are closed under certain families, called covering families, if you like. And as it happens, that groupoid is etale. And we come to a diagram like this. I want to point out this diagram 1 you're looking at here. Takes a pseudogroup and passes it to an etale groupoid that I just mentioned. And then that, under the B construction, passes that to a topos. And something else, which is denoted with that delta symbol there. You see, toposes alone are not enough. The category, as it turns out, this analysis of pseudogroups, passing from pseudogroups into toposes, it's not enough to just consider toposes. We need another conceptual device, which I'll call a coordinatized topos. Top plus. See the plus, we use plus is a good symbol because it looks like a coordinate system, right? Plus. But anyway, it consists of it's a very simple conceptual device. It's a topos and a globally supported object of it. And this has suitable morphisms and so on. So,
X is a function from the topos of functor. What is globally supported means that it's not 0? What is that globally supported mean?
Oh yeah, no, X is an object. It's a globally supported object of E. Globally supported means it's mapped, technically it means it's mapped to the terminal is an epimorphism. Yeah?
Yeah, okay.
And so this top plus, we call that the category of coordinatized toposes. So the analysis of morphisms requires this. This is not a, this is a require. We found this as a necessity. Anyway, the main point I'm trying to make about this diagram 1 is that here we have this passage from pseudogroups into coordinatized toposes. We want to understand it independently of etale groupoids. In other words, we want to take this out. We want to simply, from a pseudogroup, pass to its topos, thinking that S is somehow a site or a prescription for that topos. And thereby we get and in doing so, we would like to understand morphisms very, very carefully. Another aspect of this, an important aspect, is that there's a passage back, an adjoint here, which I'm going to call I. It takes a coordinatized topos, right here I'm looking at, which is a topos and a globally supported object, and produces a pseudogroup. This is the basic Koch-Mordic construction. They do not describe it this way, but that is how we describe it in our paper. It's the opposite. So this is the main connection I'm trying to illustrate here that we analyze. And I should say now what this I is. It's a pseudogroup. It's an important, I'm glad you mentioned I of X because it's like that. I remember I mentioned I of X before. Well, this I of E of X is a similar idea, but we use a different terminology. We use the terminology bisection a bisection on X on an object X, if X is an object of topos, then let us say that a bisection on X is an equivalence class, never mind that, but it's a pair of monomorphisms like this. So this is very reminiscent of the IX, but instead, now we're talking about a topos E. So it's a general construction. If E were the category of sets, say, then that would be the IX we talked about before. It would be precisely that. And so on. So a bisection on X is an equivalence class of pairs of monomorphisms like that. And two such pairs would be equivalent if there's an iso between them. Yes. So let's say square bracket denotes equivalence class, and star is a very simple operation. You just reverse M1 and M2. That makes a pseudogroup. And it's quite interesting. This up to Morita equivalence one can show that every pseudogroup is Morita equivalent to one of these symmetric ones, and moreover, by a coordinate preserving equivalence. I know I haven't explained yet what are these coordinatized toposes. Well, actually I did. I said exactly what is an object in that category, but I didn't explain what is this what is this coordinatized topos? What is that delta thing or that gamma thing? Well, these are technicalities we'd have to get into later. Of course, I don't think we'll have time for that today. I've already gone on a little bit. So that was our first goal, to understand this B of the germ groupoid G of S in very kind of concrete terms. And we did under the topos of etale actions on the germ groupoid, and we call that topos B of S, simply. So we need a site for that topos, and this may be described actually in a very simple way in terms of Grothendieck topologies. So that was our first goal, and we did that. Our second goal, that this puts us in, we're now in position to achieve our second goal, and that is to determine what the topos of a pseudogroup classifies. So if you want to know what we mean by that, we want to know what are geometric morphisms into the classifying topos. And we prove the theorem now. We define, in terms of that concept, you know, S into I of X, we define torsors in those terms. Maybe I'll have to go back to the whiteboard to explain that more. But the classifying theorem looks like a statement like that. Only now, we're not restricted to localic models. It's arbitrary models, I should say this, and arbitrary morphisms between them. So this is not a groupoid anymore, as it is when you, of course, when you just confine yourself to isomorphism, you have a groupoid, but these are not groupoids in general. And furthermore, since every topos, every étendue, I should say, is a B of S, you in effect get a statement about what étendues classify. So as I was saying, our work is all based on a close analysis of how pseudogroup morphisms pass to geometric morphisms. As a matter of fact, and the passage is contravariant, by the way. So that's an overview of the paper. I've gone on now for a while. I can get into the details. Of course, I don't have a lot of time. So I think what I'll do is say at least what is a torsor for a pseudogroup. So I'll have to go to that section. If I can remember where it is. I'll have to stop there. I can. It's not working for me. Oh, I'll just page down, I guess. Actually, here's a definition of a formal definition of a pseudogroup. Right here. It's an inverse semigroup in which every compatible just subset of it has a join, every compatible. And moreover, multiplication must cooperate in this sense. Anyway, let's go to what is a pseudogroup torsor. It's interesting, now that you know that this I of X is a pseudogroup, you might ask, well, what is that? What is the topos of such a pseudogroup? And this gives you a good idea of why coordinatized toposes are necessary. As a matter of fact, what do you think the topos of this IX is? It turns out that it is sets. The topos of a pseudogroup is sets. Here, sheaves of X stands for the topos of a pseudogroup. It's sets, no matter what X is. If X is not empty, so that says that, wow, toposes are no good for this. Because every pseudogroup of that form I of X has the same topos. That is why coordinatized toposes are necessary. And in fact, the coordinatized topos of I of X is set paired with the object X, the set X, the coordinatization X. So I'm trying to find the definition of a pseudogroup torsor. Actually, I'm not sure if I can find it. Just let me look around for it here. Must be later. Where is it here? Oh, here it is. Here's my section. So let me conclude just in order to emphasize that this concept here is indeed at the center of things, the way we see it anyway. An S set, by which we mean if S is an inverse semigroup, by an S set, I would mean a pre-homomorphism from S into I of X. So it's a set X and a pre-homomorphism of inverse semigroups. But when we say it's a local action, we want to say also that it's a pseudogroup homomorphism. By that, we mean it preserves compatible joins. So that brings us to what a pseudogroup torsor is, at least in the category of sets. Care must be taken when defining this notion in a topos in general, and we need to do that. But anyway, it's a non-empty local action that is transitive and locally free. Transitive means what you think it means, and locally free, it's like free, but only locally so. Which I didn't explain, but anyway, in a previous definition. So that's what's meant by a torsor for a pseudogroup. This concept works for pseudogroups. Actually, maybe I've already used up an hour. I didn't want to go on much longer than that. There's much more to explain. The nice thing about this is it turns out there's a nice connection with pseudogroup homomorphisms in the sense, morphisms of pseudogroups, and that a pseudogroup torsor is precisely a flat pseudogroup homomorphism, meaning what's called preserves binary infimum and what is called in Marx, what Marx introduces as the term hypercollitic. But that is precisely what we call a flat pseudogroup homomorphism, meaning preserves binary infima and hypercollitic, which I didn't explain what that is, but anyway, that term hypercollitic was introduced by Mark Lawson. Turns out, actually, it's precisely equivalent to transitive, that term hypercollitic. It's precisely, in this case, a mu like that is hypercollitic, if and only if it is transitive. Yeah. That's an interesting little connection. Anyway.
John, is there an intuition why I of X is set?
Oh, yeah. Okay, let me go to the whiteboard. I guess I'll stop there. I've talked long enough about it, although there are many technical details that's quite that I would love to go into, but the time is, I've probably gone on long enough.
Yeah.
But let me just try to answer your question by going back to the whiteboard here. I can't write, unfortunately, on the PDF. I'd like to do that.
You know, next to the yellow, okay, fine. So right on the blackboard, on the whiteboard.
Yeah. So as I was saying, yeah, it's interesting. I of X, if X is a non-empty set, I of X, this thing, B of X, which I just call B of I of X. We just, for short, we write it. And that in turn is a shorthand notion for B of G of the germ groupoid of it. But anyway, B of X. As it turns out, it's set. And actually, I think maybe I can give an intuitive idea of why this is always so. But before I do that, let me mention that it seems that therefore topos theory is useless, because the topos of all these inverse semigroups or all these pseudogroups is set. It's all the same. That is why we need our coordinatized toposes. And as it turns out, we are saved by this notion. We are saved by it because B of X does not equal set. B of X, I mean the pseudogroup IX does not pass to set. It passes to the coordinatized topos set with its presentation X. X is a presentation of the topos set. And you might wonder, how is that? And that, I think, answers your question, Nosen. You see, this topos has a generic point. It's sort of like saying intuitively, X is some sort of space, and it has a generic point. It has a single point in which, here's X. It has all, I know X has lots of points. But actually, B of X believes that all these points are essentially the same, and that therefore it has a generic point. Yeah, and it does. So how could a set have a generic point and not be one? So in a sense, or another way to put it, I could get into more technicalities. That's maybe a poor explanation. But if you regard, I'll try to go on a bit here about this. If you think of I of X as just an inverse semigroup, then its category is kind of, think of the groupoid of subsets of X. The objects are the subsets of X and isos between them. That's a groupoid.
Yeah.
Yes?
Yeah.
It's a groupoid. It's a groupoid with no topology or anything. It has a topos, which is not set. It has a topos, but that topos has a generic point. Let's call this topos, I don't know, something different. I don't want to call it B of X, but it has a generic point. Okay, I'll just call it, if that's a groupoid, let's call it just G of X. This topos has a generic point. It corresponds, this is pre-sheaves on a category LX, where LX is the subsets of X, same objects, but just monos. So LX would be monos. It's a lengthy explanation, I know, but it's monos between them. That would be LX. So this topos has a generic point corresponding to a flat functor here. And it's simply the subset A of X maps to A itself. Yeah?
Yeah.
It's a flat functor. It's flat. It corresponds to a point of this topos. It's a generic point. What that generic point is telling us is that all the points of X are the same. Okay. So when you take when you take sheaves, the actual topos of X from the pseudogroup point of view, that's going to be a sheaf topos. And when you take sheaves, you're forced to conclude that that generic point is actually an equivalence. So that's my best explanation. That's actually a more technical explanation. But basically, intuitively, pseudogroup perception of IX says that all the points of X are the same. That's the intuition there. Yeah, that's why.
Sounds good. Any other questions?
That is my explanation. This is the pseudogroup explanation of that. But anyway, thank you for the question. I think I'll stop there.
Okay.
That's why we need coordinatized toposes. We must keep the object X, which coordinatizes set, because how am I going to recover the pseudogroup from a topos alone? You have to have its coordinatization. But
what is set if it was coordinized?
What is set? What do you mean?
What is set with an X, with a globally supported X? What is that?
Oh, it's just a pair. It's the category, the topos of sets paired with a non-empty set X.
Any non-empty set would do.
Yep. It's as simple as that. Yeah. X is a coordinatization of set in this sense, in this pseudogroup, in the pseudogroup sense, I guess. So this conceptual device turns out to be necessary. So indeed, X is not lost. It's just a little unexpected, though, that under this correspondence, which I'll go back, maybe I'll go back to the, under the correspondence at the very beginning, here, you see, it seems like if we didn't use top plus there, we would be sunk. There would be a useless, but it's not, because the pseudogroup, the symmetric pseudogroup on a set X goes to set paired with its X as the coordinatizing object. That's right.
All right. Thank you very much, Jonathan.
So that is the end. Thank you. Thank you for your attention.
Marta Bunga's on. Hello, Marta. Welcome.
Oh, hi.
How do we give a reaction? All right, give a reaction. Anyways, any other questions? Marta, you're mute. You have to unmute yourself.
Where's the chat?
On the bottom, it says where on the bottom left where it says mute. There's a line across it. The bottom left of your screen, Marta.
What do I? Bottom left? Oh yeah, I see it. Yeah.
I saw it. Okay. Do you hear me now?
Yeah, I hear you now. Perfect. Hello.
Oh, hi.
Yeah, well, I have nothing to say because I just joined. I mean, Jonathan, this paper, can I have it or something?
Well, you missed.
Yes,
I
about
your paper at the beginning.
right? Sorry.
I spoke about your paper at the beginning. I can actually go back to that slide if you like.
But,
she wants the paper. You'll email her the paper, yes?
When is it up on archive, I think is the question.
I cannot read it. I cannot understand anything, all right? Okay, I'm sorry.
Now, wait a sec. I can go back to my first slide.
Paper, Jonathan.
Well, I don't want to disturb you. I just say, can you send me this paper?
Oh.
He's going to email it to you.
Oh, can you see the paper?
Okay, well.
Yeah, I mentioned your paper here at the beginning, yeah.
Mm-hmm.
It's related.
Yeah, I can
down here.
Yeah, right. Indeed. What?
Well, I'll send you this.
And I'm interested, yeah, right. Okay, please. Sorry.
It's related, yeah, of course.
Yeah, that's what I thought, but you know, I couldn't.
So I can certainly send it to you, yeah.
Right, right. Mm-hmm.
Actually, there were many papers that were, I wanted to mention that there are several papers that inform our paper. Yours is one of them, of course. But yes. I wanted to mention, so I can, what the heck, where's my...
Now I don't see anything. I see something saying Zoom.
Oh, the whiteboard, yeah. Pardon me. I went to the wrong screen, yeah.
Okay.
Well, I'm finished talking about it, but my very first slide, I was mentioning There it is. All the different papers that inform our paper.
The MB is you. Mark.
Well, it could be many other people, but yeah.
Oh, well, there are several. There's Peter in my paper first. There's a paper by Lawson and Lentz. The Koch-Mordic paper.
I haven't seen any of this in a year. Not a single word of math in a year. So, okay, I'll get back.
The paper of Pedro.
I'll get back.
Anyway, this is the recent history of the topic.
Absolutely. Absolutely. Yes. Yes.
So,
I understand.
but anyway, the talk is recorded, I think.
Right. John, you have a question in the chat.
Yes.
If I have the category of opens of a space, what does the coordination on a topos correspond to?
Yeah. Okay. Let me go back to the paper. How come I can't see the question? Where's the question?
It's on the chat. You got to go down on the chat. It says chat.
Okay, Zoom. I must, share the Zoom. Yeah. And here's the chat, okay.
No, that's not the chat. That's not the chat.
Don't worry about the question. Is just, if you have the category of opens of a space, what does the coordination on the topos correspond to?
Oh, I think it's just the, And no, but what are your maps between them? Those are the objects, but what maps are you talking about between them?
Well, the category of opens on a space, right? So that I mean, it's not my question. I'm interpreting. So
the inclusion maps, presumably.
Yeah,
it's the inclusion maps.
No, the homeomorphisms between them. Is that what you're talking about? Like, what pseudogroup are you talking about?
It's just a pseudo group that is a frame, the frame of opens.
No, but really? Oh, well, that's just that is the space. That's the space. That's the sheaf topos.
And what's the coordinatizing object? That's the question.
One.
What
Could
is
be one.
the object in that case?
Yeah, I think it's one. Yes. If you're just talking about the idempotence, okay, that frame, the frame of opens as a pseudogroup, as a frame, yes, the coordinatizing object is one, the identity, the terminal object. Yeah.
Okay, I think we're done. Anyways, Jonathan, thank you very much. It's very interesting. So next week we're meeting at 7, not at 6. And Andre Rodin is going to talk about Vovetsky's unfinished project. You're all welcome to join. Okay?
Stop sharing.
Okay, you stop sharing.
So, Nosom, will you please send a message,
Sure. But I'm sorry, we changed the time because John is far away.
No, I'm not.
You're not in New York, are you?
No.
No, okay. Anyways.
Well, it's nice to see you. That's all I can say. I'm sorry.
I'll give you a hint.
Anyways, okay, ladies and gentlemen.
Plastic money.
It's a pleasure. We'll see you all next week.
I'll read it, Jonathan, and I'll email you or something, okay?
Yes.
I will read it when you send it, and then.
Yeah, okay, yeah, I will. I'll send it to you right now.
Please, okay.
Good to see you. How are you doing?
Fine. I mean, what else can one say, right?
Right.
It's the best one can say. Yes. Yeah, and you? Okay, fine.
I'm working, it's work, I have to do a lot of teaching and so on.
This is not what this is meant to be, right? But
you can take advantage. Yeah,
yes,
I have a lot of
sure you do. Yes, I'm sure you
duties.
Do. Yes,
and
I haven't left the apartment in 7 months, to tell you the truth. So that tells you something. Okay. Anyway.
It's spiking again in Montreal, I hear.
Well, maybe I was going to go